Morning, good afternoon, and good evening. Today, we are going to be covering the fifth subtopic of Topic 1 motion called effects of forces. What is a force and types of forces? A force is any influence that, when unopposed, will change the motion of an object. Forces are a vector quantity. Forces occur when two or more objects interact. There are two types of forces. Contact forces. Objects are touching, such as tension, as two people pull against one another using a rope. Non-contact forces. Objects are not touching, such as when the force of gravity acts even when the objects are not touching. Contact forces versus non-contact forces. Contact force examples are friction and air resistance / drag, tension, normal contact force, and upthrust. Examples of non-contact forces are weight or gravitational force, electrostatic force, and magnetic force. Upthrust. An object that is partly or completely submerged experiences a greater pressure on its bottom surface than on its top surface. This causes a resultant force upwards. This force is called upthrust. Rising. If the upthrust is larger than the weight of the object will rise. This happens when you jump into a swimming pool and then rise back up to the surface. Under the surface, the weight of water you displace, the upthrust, is more than your weight, so there's a resultant upwards force. Floating. When your head sticks up out of the water, the upthrust reduces as your head is no longer displacing water, and there is zero resultant force, so you can float at that level. Sinking. If the upthrust is less than the weight of the object will sink. If the density of the object is greater than the density of the fluid, the object can never displace enough fluid to create an upthrust that will hold its weight up, so it sinks. Describe how forces may change the size, shape, and motion of a body. Forces may change the motion of the body to a certain direction if a resultant force is pointing to that certain direction, because force is a vector quantity. Forces may cause a change in the internal arrangement of molecules making up the object, and depending upon the magnitude of the force, the size or shape of the object may change. State Hooke's law and recall and use the expression F equals kx, where k is the spring constant. Hooke's law states that extension of an elastic object is directly proportional to the applied force. Hooke's law can also be applied to the compression of an elastic object. Hooke's law is load in newtons equals spring constant, newtons divided by unit of length, times extension, unit of length. Example of a load would be weights, and spring constant indicates how easy it is to stretch or compress a spring. Higher the spring constant, the stiffer the spring. And here, an image of the extension, what it looks like is there. It's just an extension. Plot and interpret extension, load graphs, and describe the associated experimental procedure. This is an extension load graph here, which shows elastic limit or limit of proportionality, and where it follows also Hooke's law. When line is straight, gradient is constant, it means Hooke's law is being followed. Beyond the elastic limit or limit of proportionality, the graph is no longer a straight line, and the spring is permanently deformed or inelastically deformed, as it cannot return to its original shape. Also, once limit of proportionality has been exceeded, doubling force will no longer exactly double the extension, as relationship has become non-linear. This graph shows what happens when the load is removed. The extension does not return to zero, so the spring is now longer than at the start of the experiment. Though, if the object returns to its original shape after forces are removed, it was elastically deformed. This most likely applies or applied to the removal of load of a spring that has not exceeded its limit of proportionality. Recall and use the relationship between resultant force, mass, and acceleration. Force equals ma. Resultant force, newtons, equals mass in kilograms times acceleration, meters per second squared. This is an examples question. The car accelerates from 16 meters per second to 30 meters per second in 4 seconds. The mass of the car is 1,200 kilograms. Calculate the force required to produce this acceleration. State the formula that you used and show your working. So we know it's F equals ma, and F is the unknown. 1,200 kilograms, which is the mass, times the acceleration which we will have to calculate. We know that acceleration formula equals final speed minus initial speed divided by time. So 30 minus 16 divided by 4. See what that is. Using the calculador. So that's equal to 3.5 meters per second squared times 3.5 meters per second squared. Now let's just multiply these values together, and that is equal to 4,200. So the force needed to produce this acceleration is 4,200 newtons. Friction. Friction is the force between two surfaces which impedes motion and results in heating. And you have to recognize air resistance / drag as a form of friction. This is an example question. The air in the tube is now pumped out. State how paper and coin will fall. The apparatus shown below is used to demonstrate how a coin and a piece of paper fall when they are released from rest. So what happens is, because the air would be pumped out, air resistance would not be present and acting on either object. So it would be observed that the piece of paper and the coin will fall at the same velocity and time in comparison to when air resistance was present, where the coin falls first and faster than the paper. Resultant forces. Find the resultant force of two or more forces acting along the same line. You can easily calculate the resultant force of two forces that act in a straight line in the same direction by adding their sizes together. So if it's 3 newtons to the right and 4 newtons also to the right, that means resultant force is equal to 7 newtons to the right. And then other examples below is a zero resultant force on body. You have to know that when resultant force equals 0, it means an object is either stationary or moving at a constant speed in a straight line. So this first example, where it's stationary, shows that the forces acting on it are equal to or bigger than 0, and they're equal to each other, and that's why it's stationary. In this second example, where the ball's falling down, it has terminal velocity. The force due to air resistance and the force due to gravity are equal. That's why it's no longer accelerating. It is in terminal velocity.